All right, this is the answer key for the pendulum video. So we're going to look at this conceptual problem here, which is, I think, pretty straightforward. We've done a lot of this stuff in the past. So child sits on a swing that hangs straight down and is at rest. Draw energy bar chart for the child, swing, and earth system. Okay, as the person pulls the child back in preparation for the first swing. So when they're pulling them back, they're doing some work. Okay, so this is basically the work done by the person. Okay, now for part B, at the moment the person releases the swing while it is at its elevated position. So basically, all that work, same amount, should be the same height, is basically now gravitational potential energy in the swing and in the child. Okay, as the swing passes the equilibrium. So when you pass the equilibrium, you're at the lowest point. So all your gravitational potential energy, basically everything we had here, is in the form of kinetic energy now. When it reaches half the maximum height, so at half the maximum height, half of your energy, in other words, you have half the height, so you have half of this gravitational potential energy you had here, and the other half should be kinetic energy. So those two together should add up to total energy. And then as it passes the equilibrium position, moving in the opposite direction, that should be exactly like C. So it's all kinetic energy. This question still has to do with the springs. A mass M is attached to a vertical spring, stretching it a distance d. So basically at that point, I think we can say that mg equals k times d. Then the mass is set into oscillations, set oscillating on a spring with an amplitude a. The period, okay, so let's figure out the period. The period is 2 pi square root of m over k. We can get k from here, which is mg over d. I think we can get rid of those, and it's going to be 2 pi square root of d over g. So it's proportional to that square root of d over g. Now the problems here are pretty straightforward. Okay, find the period of a pendulum of length 2 meters. So just period is 2 pi square root of L over G. So you just have to figure out what that answer is, and it should be about 2.81 seconds. Find the length of a pendulum that has a period of 1.5. So again, same formula. So 1.5 is equal to 2 pi square root of L over 10. So you can do this in a lot of ways. So 1.5 over 2 pi, but make sure you put the 2 pi in parentheses, right? You square that, and then you're left with just L over 10. So make sure you put this 2 pi in parentheses here. So if you want to find L, you just have to multiply whatever you got in the calculator here by 10. By what factor does the period of a pendulum change if the length is double? So if you double the length, so here's the formula. T equals 2 pi square root of L over G. So if we double the length, the period will be radical 2 times as much. The length is reduced to 1/4. So if you take the length and you divide it by 4, this 4 comes out as a 2 on the outside. So your period will be half of what it was. Number 28. By what factor does the length of a pendulum change if the period is doubled? So T is 2 pi square root of L over G. So if I double the period, it means I double this side. So I'll have a 2 out here. So if I put that 2 inside, it should become a 4. So the length of the pendulum will be 4 times as much. Now, if the period is reduced to 1/3, so if I do 1/3 here, the 1/3 becomes 1/9 on the inside. So the length of the pendulum will be 1/9 as much. #29, consider two identical masses, M. One is attached to a spring of length L and oscillates as simple pendulum. Okay. The other is attached to a spring and vibrate as a spring mass oscillator. Suppose the simple pendulum and the spring mass oscillator have the same period. So we're going to find the spring constant in terms of these quantities here. So the periods are the same. They're telling us that. So 2 pi square root of m over k is 2 pi square root of L over G. So which means m over k is equal to L over G, which means k is equal to mg over L. Okay, 30. An object swinging on the end of a cord as a simple pendulum with period t. Another object oscillates up and down on the end of a vertical spring, also with a period t. If the mass of both objects are double, what are the new values for the periods? Well, for the pendulum, the period will not change. Okay? Yeah. And for the spring, if the mass is double, the period is 2 pi square root of m over k. So m doubles, so you're going to have t times radical 2. And here you could have noticed that it should be just b because the period of the pendulum will not change because the mass does not affect it. And we talked about that in the previous video. Let's look at these ranking tasks. Now we're trying to rank the frequencies. So the period is 2 pi square root of L over G, which means frequency is 1 over period, which is that expression there, right? Okay, so the mass doesn't matter, so we don't care about the masses. So the only thing we have to worry about is the length of the string. So the higher or the shorter the length, the higher the frequency. Yeah. So it looks like it's C and D have the same length, so they come first, and then A and B, they have the same length and they come last, because there is an inverse relationship between frequency and the length of the pendulum. And the last one is we're looking to rank the time it takes to make one complete swing. So basically we're trying to rank the periods. So the masses don't matter again, right? So if you want to rank the periods, okay, period is 1 over frequency. So the lower the frequency, the higher the period. So B and D have a frequency of 2, so they come first, and A and C have a frequency of 3, and they come last. And that should do it.